Robert Wagner is here to talk to us about where is the moon? Getting accurate coordinates from lunar data. Robert, you are good to go whenever your slides show up.
Okay, am I audible?
Yes.
Okay. So yeah, I'm going to be talking about how to get the most accurate possible coordinates out of LROC data. Next slide, please. So the basic question, why does this matter? So landing ellipses are pretty small. The numbers I've seen thrown around the most are like 100 meters wide. And the LROC narrow angle camera shows images at the meter scale, half a meter to 2 pixels for most of our images. What this means is that landing near a very specific feature like some rock is actually a reasonable goal. Maybe not a rock, the engineers might get mad about that one, but some crater or some specific patch of regolith. So the question is, how well do we know at the location of whatever specific rock you want, which ties into, can you refer to a site by just giving coordinates? Short answer, no. And how well can you cross-reference that point with other data sets? Depends on the data set. Next slide, please. And since this is supposed to be an animation, next slide after this. Yeah, so the vast majority of NAC images are uncontrolled. That image on the left, I took the two farthest apart images of a rock at the Apollo 16 landing site and overlaid them, and you can see that that rock is appearing in two places about 50 meters apart. This is pretty normal for any site on the moon. Most of our images are positioned on the ground when you don't do any special alignment to within about 30 meters of truth, which means that two necks to be up to 60 meters apart from each other. This does require that we use the most accurate spacecraft position data from the LOLA team. That's available up through about 6 months before present. And without that, we expect errors up to about 100 meters. Quick note is that you should avoid getting coordinates from images in the early commissioning phase, so before about September 2009, because those tend to be off by about 250 meters. And another note, for people looking at the poles specifically, we've recently found that the accuracy of images within about 5 degrees of the South Pole are about 2 to 3 times those of every other image we have. We're trying to look into why this is. Next slide, please. So, quick note on decimal places. So, using a specific number of decimal places implies some precision of your, some meter precision. So, on the moon, this maps out fairly nicely. So, 3 decimal places precision means that you have a 30-meter box that those coordinates could refer to. Illustrated on the right here at the Apollo 11 landing site, that's about the size of the area the astronauts walked around in. Next slide. 4 decimal places will is about a 3-meter box, or about the size of a robotic lander. Next slide. And 5 decimal places, you're getting down to 30 centimeters, which is about the size of an astronaut footprint. So, and smaller than pixels of just about any image you can get of the moon from orbit. So, in summary, you never need more than 5 decimal places for orbital data. That's just wasted effort copy-pasting numbers. 4 is usually the best, although be warned that that is not necessarily going to be unambiguous when looking at multiple data sets or multiple MAC images. 3 decimal places is about as many as you can trust when you're just grabbing numbers off of some arbitrary NAC. Next slide. So, how to get more accurate data position than that? The best source, previous slide, of data is the NAC DTMs. These are very tightly controlled to the LOLA laser altimeter reference frame for the moon, both vertically and horizontally. For NACs made since 2013, the 90th percentile horizontal offset is about 7.5 meters. Before that, control is worse, so check the date on the DTM you're using. These DTMs all come with orthophotos perfectly registered to the terrain model at the original pixel scale, so those are the best high accuracy, high detail images you can get of the moon right now. We have seen some internal distortion in these DTMs on the order of about 0.1% distance error, but that's quite small compared to the errors you see in arbitrary NACs for offset around the moon. Yeah, there's also a pixel level map of confidence in the stereo match solution, so you can figure out how good the model itself is. Next slide. There are some points in the README that are good to look at for figuring out what your what is going on with the DTM. So a few key things are the creation date, so you can tell whether it's before or after that 2013-ish cutoff. The RMS error is the vertical error relative to Lola. Precision error is vertical precision, and post spacing is the DTM pixel size. Next slide. Now, we don't have DTMs over most of the moon because NAC images are fairly small compared to the moon, and it takes a fair bit of work to make these. We have a lot more controlled mosaics or ROI mosaics. These are probably the next best thing for accuracy. These are sets of images stitched together to minimize inter-image seams. They're tied to DTMs for absolute control where possible, or to multiple NACs to try to do some absolute control where that isn't possible. We're still working on quantifying the actual accuracy and distortion of these, but they're probably better than just arbitrary NACs. One note is that we have very few sites with photometric sequences, which are sets of multiple NACs that are tied to very tightly to a DTM. These will have very nice control on a lot of images, but there are very, very few of these sites. Next slide. So the best way to quickly look at all of the NAC images and also cross-reference with a lot of other data sets is QuickMap. There's the URL there. It's a very nice way to look at a lot of data sets. The only downside is, like any GIS software, it's limited by the accuracy of the underlying data. So once you've figured out roughly where you want to go, you'd want to do your own processing to improve your accurate estimate of where points are. Another note is that because there are over 1 million NAC images, QuickMap is working from a database of slightly downsampled JPEG compressed versions because they don't have that many terabytes of data to store stuff in. So processing your own images will get you slightly more higher detail. Currently, the most positionally accurate image data on QuickMap is the NAC ROI mosaics. We're working on, thank you, adding the DTM orthophotos, but for now, what you can actually do is locate the DTMs on QuickMap. There's a link directly to the PDS download page. If you download the TIFF file from that page, you can actually re-upload it into QuickMap. You'll probably want to use the lower resolution one. The higher resolution ones are usually too large a file for your web browser to handle properly. Next slide. So best practices for coordinates. Use NAC DTM orthophotos if at all possible. If you want to land at a specific feature, make sure that you include a picture of that feature so that it's unambiguous that this specific thing is what we're talking about. Your coordinates might not be right. They'll be close enough to find that feature, but only if you include a picture. I recommend using coordinates to 4 decimal places. Best quality, process stuff yourself, which I'll talk about on the next slide. And if you don't need to land at a specific point, say so. Engineers are very literal minded. If you provide coordinates to 4 decimal places, they will try to land at those coordinates to 4 decimal places, no matter what. Even if you only need to land within a kilometer of the place, say so. They'll be happy to land somewhere in that kilometer. So yeah, next slide. Processing yourself. We just posted on our website a very detailed guide to NAC processing, which basically covers everything I've learned about using USGS ISIS to process NAC images in the 10 plus years I've been working on the mission. Key things to remember are you do need to adjust some settings with your spacecraft position data, and you'll want to upgrade to a better model than the global DTM that's default in ISIS. There's a technique for using Ultimax to get better coordinates. Next slide. Yes, I'm running out of time. NOAA covered our export data, so yeah, just switch to the conclusion slide and I'm done.
Thanks, Robert. This is a tremendous reference for everyone. I hope everyone was paying attention.